Hello, it's Mrs. Allison. Today we are going to look at polar area, and this tends to be a pretty big topic that will show up on an FRQ pretty regularly on the BC exam. So let's start with an example first, and then, or a warm-up problem first, and then we'll move on to polar area. So hit pause, try the warm-up, and then come back. All right, hopefully you had a chance to try this problem. And it's asking us to represent the length of the path described by the parametric equation. So it's telling us the length is L. And it tells us that our x function is sine squared of 2t. And then our y function is cosine of 3t. And we need to find that length from 0 to pi over 2. So what we're going to do first is remember that our arc length, and normally we'd call it S, but they're naming it L. So our arc length goes from 0 to pi over 2 of the square root of dx dt squared plus dy dt squared dt. Okay, so what I would do first is I would find the derivative with respect to t rather, of x. So we get dx dt equals, and this is going to have quite a bit of chain, actually. I think this is a 2-chain problem. So we've got the big outside function, which would be 2 times the sine of 2t times the cosine of 2t, times 2 would be dx dt. Let's clean that up just a little bit. Let's call this 4 sine of 2t cosine of 2t. And then I know I'm going to need to square this to put it into the formula. So dx dt squared would be 16 sine squared of 2t cosine squared of 2t. All right, now let's do dy dt. So let's take the derivative of y with respect to t. So dy dt is going to be, this one will be a little bit easier, so it's going to be negative 3 with the chain, negative 3 sine of 3t. And if I square this, I get 9 sine squared of 3t. And then what I would be doing is I would be substituting in the dx dt squared and the dy dt squared into this formula. And I can see that the answer that I want is D. So this answer here is the one that I want. All right. So we've worked on arc length for quite a while, and we've talked about polar derivatives last class. So now we want to look at finding the area. And typically what happens is when we find the area, we're going to find an area that is enclosed by, not under like we typically did before. It works a little bit different. So we're going to enclose the area or find the area of some region that is enclosed. So one of the first skills that we need to be able to have is to be able to find the points of intersection. Sometimes this can be done on a calculator, but oftentimes this is almost easier done by hand. So for example, if I want to find the points of intersection of the following, the points of intersection that I could be finding, or that I will be finding, would be the points that are where the two functions intersect. Now, this could be used for several different things. This may ask me to find the area sandwiched in between here, in which case I would need to know the points. It may ask me to find just the area on the red side that doesn't include the blue, or just the blue side that doesn't include the red. So we need to be able to find those points of intersection. And truthfully, the easiest way to be able to do that is just to set the two equations equal. If r equals 2 plus cos theta and r equals 2 minus cos theta, then we have a pretty easy equation here where 2 plus cos theta equals 2 minus cos theta, and then we start to get the numbers on one side and the cosine functions on the other. And rearranging this, I get 2 cosine of theta equals 0, which means the cosine of theta equals 0, which means theta could be pi over 2, theta could be 3 pi over 2, theta could be negative pi over 2, and it all kind of depends on the direction that we're going. And we could keep going. Typically, we look between 0 and 2 pi, which is why I'm not extending this beyond pi over 2 and 3 pi over 2. Now, if we talk about these points, these 2 points are ordered pairs. Remember, our ordered pairs always are r, comma, theta. And so if we look at these ordered pairs, I have the ordered pair here that would be 2, comma, pi over 2. And then I have the ordered pair here that would be 2, comma, negative pi over 2. And those would be my ordered pairs. So those are the points of intersection of the graphs. Now, let's talk about this area. Once we have been able to figure out our points of intersection, then it will be that'll be the first step in finding the area. And so we said that we need to notice that we're finding the area that's enclosed by instead of under, as we typically have done in area problems. We're not finding the area under the curve, although we're going to use that idea. They work a little bit different in polar coordinates, and here's why. When we sketch a curve, so we may have some polar curve that looks like this, okay? And what happens is we don't know what that curve is. We know that we want to find the area between 2 different angles, where theta equals this alpha angle and theta equals this beta angle. And we want to find this area that's made up by those curves. Okay, let's do a little bit of recall of what we already know. If we recall that if I have some graph and I want to find the area under this curve, we started out by doing this by finding tiny rectangles, remember? And we said, okay, the area here equals the base times the height. And then we said, okay, well, really what happens is that this area is the base, which is this tiny little sliver of x that we call dx, times the height. Well, the height of this rectangle here would be the function value. Now, we would write it in a different order. And then what we said is we're going to keep adding all of these rectangles together. And we know then that the area is going to be equal to the sum of, or the integral of, from a to b of f of x dx. That's how we found our area. That rings a bell, correct? Hopefully. What you should also recall, and this goes back just a little bit further, is from geometry. We know that the area of a circle, if we wanted to find just the area of some sector of the circle, so not actually the whole circle, just this sector that's right here. If you remember back to geometry, we said that to find the area of a sector, we take and do theta, we'll call this angle theta, divided by 2 pi times pi r squared. That's how we found the area of a sector. And then we simplified it and said, okay, that area of the sector is going to be 1/2 r squared times theta. 1/2 r squared times theta would be the area of that sector. Now let's combine those two ideas and look at our polar curves. This time we are going to divide our region not as rectangles under a curve, but more like the idea of an area of a sector. And we are going to divide, and we're going to pretend I can draw straight, and we're going to divide this region into multiple sectors. And we're going to look at them as if they were these tiny little sectors that we've created. Now, we're going to make it so that this angle is so small, we'll call it d theta, we're going to make it that this angle is so small that essentially they are sectors. They would be just like the sector. Just like this in our area is essentially a rectangle. Although we know the shape of the curve may not be square, we do know that we can create sections that are so small that they are essentially rectangles. We're going to do the same thing here, only we're going to create essentially sectors. And what I know is that this is d theta, this is r, would be my radius, and because this is some polar curve where this dimension here is r, then what we know is that this area of this sector right here, this one in green, this area of this sector would be this 1/2 theta r squared. And if I take and add all of those tiny pieces, that's what I get. Now my area for this particular sector is going to be, 1/2 r squared d theta rather than just theta, because we're taking that tiny, tiny amount of theta. And so if I want to find the area enclosed by polar curves, I use the formula 1/2 the integral from alpha to beta. We typically use alpha and beta with polar, r squared d theta. It's the sum of all of these tiny sectors. Just like this was the sum of all my tiny rectangles, this is the sum of all my tiny sectors. And that's how we find the area enclosed by polar curves. Okay, well, let's look at an example. This first example says that we want to determine the area of the inner loop of r equals 2 plus 4 cos theta. Now, when we look at this is the inner loop that we are going to find the area of, is right here. Okay. Now, what we have so far as our equation goes, is we've got 1/2, equals 1/2 the integral from alpha to beta of 2 plus 4 cos theta squared d theta. And that is my formula. Now, we need to find the theta bounds. Okay? We need to figure out what those bounds are on theta, on that integral. We need to figure out our alpha and our beta. Now, before we actually figure out our alpha and our beta, I want to look at the graph of this. And we talked about briefly in our notes on 9.3, just looking at polar curves, that one way that we can come up with our polar curves is just to plug in usually our quadrantal angles. So 0, pi over 2, pi, 3 pi over 2, 2 pi, and just see what happens along this curve and see if we can figure out what our bounds might be. Now, if we go through and look at our bounds, and I plug in 0, for example, 0 into my equation, I would have 2 plus 4 cosine of 0. Well, the cosine of 0 is 1, so 2 plus 4 would give me 6. So 0, 6 is this point right here, and that makes sense, that would be 0, 6. And then if I plug in pi over 2, plugging in pi over 2, we would get 2 plus 4 cosine of pi over 2, which would be 2 plus 4 times 0, which just gives me 2. And it makes sense that that point's right here. And so we can see that this curve is going up this way. Now pi, if I plug in pi, plugging in pi, I get -2. And with that negative radius, with pi should be over here somewhere on this axis right here. But with a radius of -2, it bounces it back here. So this point right here is -2 pi. Maybe I'll fill in these other points, 2 comma pi over 2. And then this would be the point 60. Okay, and we could keep going. This came around here. It's going to go back up and around. I would bet that 3 pi over 2, if we substitute that in, we're going to get 2 plus 4 times 0, which is 2. And then 2 pi, we're going to be back to 6. So we can see the path that this is taking. It starts here, loops around, and then loops back up to 6. Now the problem is this doesn't really give me any information about my bounds. So let's figure out what those bounds might be. What is the value of my alpha, or my theta value is what I'm really looking for. What is the value of theta when I get right here? Or what is the value of theta when I come back around right here? What are the angles that give me that? And it's really hard to tell. I mean, I can't just look at it and guess, so I'm going to solve for it. Here's how I'm going to solve for that. What I'm going to do is I'm going to set up where r equals 0. r equals 0 is right here because there is no radius outside of that. We're just at 0. And where r equals 0, we get 0 equals 2 plus 4 cosine of theta. Now solving this, we get the cosine of theta equals negative 1/2. And from my unit circle, I know that then theta would need to be either 2 pi over 3 or 4 pi over 3. And in this case, these are going to be my bounds. These are going to be my bounds of integration. So my arc length here, we're finding area, sorry. My area here is going to be 1/2 the integral from 2 pi over 3 to 4 pi over 3 of 2 plus 4 cosine theta squared d theta. Now, with the curve that's happening here with that particular my function, my polar function, this would probably be a calculator question. And so then we would substitute this into my calculator, just plug it in, go into math, go down to number 9, and substitute that in, and that's what we'd get. Now, I want to show you another way we could do the same problem. Same problem, just a different method. What if we use the idea of symmetry? All of these graphs are symmetrical. So what if instead of just finding that whole area, I work on finding half of the area? So what if I work on the first values that my function comes to? Okay, because remember, this graph comes around this way and goes under here and then comes up around the top part of the loop. I could write this, and symmetry is a great way to find the area on some of these. I could write this as 2 times 1/2 times the integral from 2 pi over 3. Now I'm using the 2 pi over 3 because that would be the first theta that it comes to right here. 2 pi over 3 to pi. We said that this point right here was pi of my 2 plus 4 cosine theta squared d theta. And if I substitute this into my calculator, what you should see is that we get the exact same answer. So using symmetry can be a great way to find the area enclosed by a curve. All right, well, let's move on because oftentimes we'll need to find the area between two polar curves. So let's look at that. As we looked at before, we are finding the area of infinitesimally small sectors and then adding up all those infinitesimally small sectors to form the area enclosed by the polar curve. Well, we're going to do something very similar here. So the first thing I'm going to look at is that if I were to find the area of, say, this first curve, r sub naught equals g of theta, if I were to find this first sector, we'll do it like that, we know that the area of this sector, this would still be d theta, would be 1/2 that r sub naught squared d theta. Now, if I wanted to find the area of the smaller region right here, this too would have an angle of d theta, but my r value is going to be different. And this one would be the area equals 1/2 r sub 1 squared d theta. Now you can imagine that if I want to find the shaded area, the green area, and I just take and subtract, oops, that's not what I wanted. If I take and subtract the two areas, you can see how I would get that green shaded area. And so this particular area here is going to be, of the shaded region, is going to be 1/2. And then I would need to do r sub 0 squared minus r sub 1 squared d theta. I'm finding the two areas and subtracting them to be able to get that shaded area. And so the area between two polar curves is this 1/2 from alpha to beta of r sub 0 squared minus r sub 1 squared d theta. Okay, so let's look at an example, because this can get a little bit weird based on where we're actually finding the areas of. So let's look at one. This says we want to determine the area that is both inside r equals 3 plus 2 sine theta. That's this blue curve right here. And outside r equals 2, and that's this circle right here. So at the same time, it needs to be inside the blue but outside the red. And so we're trying to find this green shaded region. Now, one of the things that we need to do first is we need to figure out where these points of intersection are. So to figure out the points of intersection, this point right here and this point right here, the easiest way to do that is going to be to set these two equations equal to each other. And so then we get the sine of theta. If I subtract 3, I'd get -1. Divide by 2 gives me -1/2. And so we get theta equals 7 pi over 6 and 11 pi over 6. But let's picture the unit circle for just a moment. If we were to trace around the unit circle, and I were to count 7 pi over 6, it makes sense that 7 pi over 6, let's do this in green. It makes sense that 7 pi over 6, I'm not sure which color to do this in, would be right here. That angle makes sense. It makes sense that that's 7 pi over 6. Agreed? Now, if I wanted to find 11 pi over 6, it makes sense that this is 11 pi over 6. Agreed? Now, the problem is, if I were to write my integral right now, and I said that I wanted the area to be 1/2, the integral from 7 pi over 6 to 11 pi over 6 of this r sub 0, so the outside would be 3 plus 2 sine theta squared minus 2 squared. Put that all in parentheses, d theta. If I did this way, I would be finding the area that's between these two. So I would be finding the area between these two angles over here. And that's not what I want. I want to start here and find all of these areas that are enclosed. So I'm going to change my bounds of integration because I don't want 7 pi over 6 and 11 pi over 6. In fact, I don't want to start at 7 pi over 6 at all. I want to start here. So how can I represent this with an angle that would indicate I'm going to start here and then end up at 7 pi over 6, but still go that same amount? Hopefully you think that that should be negative pi over 6 to 7 pi over 6. That will give me the correct area that I'm looking for. And so what I'm going to do now is I'm going to plug this into my calculator to get my area. And when I plug this into my calculator, I'm going to get 24.187. So 24.187 would be the area that is both inside r equals 3 plus 2 sine theta and outside r equals 2, or that shaded area. And that, my friends, is polar area. So you have a worksheet where you can practice some of these polar areas, and we will see you soon.